Let's move on to the next example, shall we? So here we've got nitrogen flowing through a diffuser, and they've given us the exit velocity or I'm sorry, they're asking for the exit velocity and they're asking for the ratio of areas. They've given us the inlet pressure, inlet temperature, exit temperature, and the inlet speed. They've given us one more thing, which I've actually forgotten to write on my givens here. Can you catch it? Go ahead and pause. Take a pause and go ahead and copy down the given information, but then also see if you can catch what is it that I've missed as I've recorded the given information here. Go ahead and pause. All right, do you see what I missed? What do your adjectives tell you? We talk about that a lot, right? What are your adjectives telling you? Always know what an adjective in a problem statement is telling you. Here we've got this problem statement saying nitrogen flows steadily through an adiabatic diffuser, given inlet pressure and temperature, and given exit pressure and temperature. If nitrogen enters at 200 meters per second, determine the exit velocity and the ratio of areas. Again, what do those adjectives tell you? Adiabatic is an adjective. We've got to know what that means, just like what steady flow or steadily means, um, just like what a rigid system or rigid tank means. There are all these adjectives. We're going to have to know what they mean because they tell us something very important that allow us then to solve the problem. Okay, so here's what I'm going to do. I'm going to have you at this point. I'm going to ask. All right, well, what's a good tool for finding? Well, I guess let's go ahead and walk through it. I was thinking I'll have it pause because this one's a little bit different. Let's just go ahead and walk through this. How do we find either V2 or the ratio of areas? You can pick which one you want to go after first. And here's what I would ask my class. Okay, what do you want to pick first? What do you want to go after first? And maybe somebody will say, well, let's find the ratio of areas. But a lot of times people will say, well, let's try to find V2. Okay, cool. What's a good tool we might have for finding V2? And somebody might say, well, what about the mass flow rate? Okay, what about conservation of mass? The mass flow rate is a part of the conservation of mass equation. Mass flow rate, we know, is area times speed divided by specific volume, or multiplied by density if you don't like specific volume. I'm going to use specific volume here because we're dealing with a gas. Okay, well, let's look here. I know a speed at 0.1, right? So I could put ones on all these. I could also I could put 2 on all of these. Remember, this is a steady flow control volume, right? They did tell us that. They tell us the nitrogen flows through it steadily. What steady flow tells us is that the mass flow rate at the inlet is equal to the mass flow rate at the outlet because there's one inlet, one outlet. It also means that the energy change for the whole system is going to be zero. All the DDTs go to zero. We talked about that in lecture 11. So I know the inlet speed and I'm looking for the exit speed. Now, if I know the areas, this might work because I might have tools to find specific volumes. We'll talk about that in a second. But I don't know the areas here. But notice this one does ask for the ratio of areas. So if I know both speeds, which I'm going to have to find anyway, and I have some way of finding specific volumes, I can find the ratio of areas given this equation. So I think we'll use this one later. But I don't think this is going to get us to V2. I think there's too many unknowns here because I don't know the mass flow rate. So I'm not going to be able to just say m dot equals this, and then given the area, I can solve this directly. But I don't know m dot or the area. And I don't know if I'm going to be able to find either one of those. So, all right. So what's another tool for finding V2 then? Well, then I'll wait. I'll pause until somebody comes up and somebody say, oh, what about the first law? Okay. Now here's where I am going to pause and tell you, write your first law equation, and let's see if you match what I've got. This is good practice. Write your first law equation and then come back. Okay. All right. How'd you do? Well, know how I did. I made a mistake. I drew a nozzle at first. Remembered, wait, is it a diffuser or a nozzle? Oh no, this is a diffuser. Might be a good thing to write on your givens up here. Duh. Right. I've got a nitrogen diffuser. All right. I write N2. You could write out nitrogen if you like, but I remember nitrogen is a diatomic gas. So I'm just going to write N2. So it's a diffuser. So I need to draw it this way, not that way, this way. Going to a larger cross-sectional area. Right. And I said, write your first law equation. So what are the energies crossing the boundary? Well, I've got energy of mass coming in. I've got energy of mass coming out. It's steady flow. So that means the change is zero, right? And then if I expand that out, I've got one inlet, one outlet. So it's a common M dot. H1 minus H2. Again, I'm calling one the inlet, two the outlet. People ask, hey, Steve, why is it 1 minus 2? Should it be 2 minus 1? Well, on this side of the equation, it's in minus out. So right now it's 1 minus 2 because I'm calling the inlet 1 and the outlet 2. Remember, it's in minus out. Don't think about it 1 minus 2. It's in minus out. That'll help you later. Okay, so I've got a change in enthalpy. How do I know that? Well, I've got an ideal gas and I've got a change in temperature, so I've got a change in enthalpy. I also have a change in kinetic energy because it's a diffuser. By definition, I have a change in kinetic energy. And oh, by the way, what the heck are we looking for? We're looking for V2. This gives me a path towards V2 because I know V1, right? And somebody's probably going to say in the comments, hey, Steve, isn't that unrealistically high? Maybe, probably at this temperature, especially when we look at what V2 we're going to calculate. It's a textbook problem. I'm not going to claim to, I don't know. Right? Yeah, no, it's probably a little high, but I don't know if it's unrealistic, but I didn't make the problem up. I'm just solving. Okay, cool. What do we know here? Well, how do we find H's? Well, H's are a property. That means I got to know what my substance is and follow the rules for that substance. I've got nitrogen. That's a gaseous substance. So I'm going to treat it like it's an ideal gas. For ideal gases, H's and U's are functions of temperature. Knowing the temperatures means I know the H's. If you don't have that memorized, that's okay, but you do need to get to where you understand that process flow of how do I find property? Well, I need to know the substance. It's an ideal gas. Okay. I need to use rules for ideal gases. If it's water R134, I need to use the rules for using property tables. If it's solids or liquids, I need to use the rules for using solids and liquids accordingly. Okay, that's kind of how that process works. What's the property? Well, what's the substance? Okay, follow the rules for that substance. I know V1, I'm looking for V2. So I think I can quantify H's. I know V1, I'm looking for V2. What do I do about M dot? Right? So here's a good place. I'm going to tell you pause it and come back, go back in your notes, see if you can figure out what can we do with M dot, because I don't know M dot. Can I find M dot or can I somehow work around it? So go ahead and pause and come back with an answer for that. Okay, do you have an answer? You might have noticed in a previous problem, I said if you don't know the mass or the mass flow rate, what happens if I divide by mass? Notice what happens if I divide by mass. If I work the problem per unit mass, so I'm going to move m dot to the other side of the equation, so it's delta H, or I'm sorry, H1 minus H2, negative delta H, plus the kinetic energy change, V1 squared over 2 minus V2 squared over 2, is going to equal 0 divided by m dot. Well, is m dot going to be 0? No, that doesn't make sense. If there's no mass flowing through this thing, it's not actually doing anything, so that doesn't make sense. So m dot cannot be 0. Since m dot is not 0, we can say that 0 divided by anything non-zero is still 0, and the mathematicians don't get too mad at us for saying, oh, we're just going to cancel that m dot out. Kind of, yeah, but we are just saying that 0 divided by anything that's not 0 is still 0. Right? So now m dot goes away. I can work the problem per unit mass. I don't know m dot, but we're going to try to solve around it and see if we can get to a solution without it. And I think in this case we can. Okay. How do we find H's? Well, you can use property tables for them. We do have, if you have ideal gas property tables where you just need to know the temperatures and that'll give you the H's. That's fine with me. I'm probably going to use C sub P. I'm going to say that C sub P at the average temperature multiplied by this temperature change, T1 minus T2, is going to substitute in for this delta H. Again, you're welcome to go look up table properties. That's fine. Doesn't bother me at all. Plus V1 squared over 2 minus V2 squared over 2 is equal to 0. What the heck are we looking for? Oh yeah, we're looking for V2. So solve for V2 now, because I think I can work with this. So I'm going to move V2, this kinetic energy term, to the other side of the equation, so it picks up a positive sign, and then solve for V2. V2 is going to be equal to square root of some stuff being 2 times quantity, 2 times everything, C sub P at the average temperature times T1 minus T2, and then add to it the initial kinetic energy V1 squared over 2. The whole thing gets multiplied by 2, and then the whole thing gets square rooted. That's not an uncommon expression we'll use. It's pretty common. You'll need that for anytime I've got an adiabatic nozzle or diffuser. Right? Okay. What else we got? So this is a path to finding V2, one of the things it's asked for. What else is asked for? Well, I'm also finding the ratio of areas, which notice I can use this expression here to find that ratio of areas. A1 over A2. Again, I'm solving this for the ratio of A1 over A2. So A1 over A2, I'm going to group like terms together, and that means I'm going to put on this side of the equation little v1 over little v2. And I'm going to put, oh, sorry, you can't see that. I'm going to put then big V2, the speed, divided by big V1, the initial speed. And I'm going to be able to find V2 here. Now, what about these guys? How do I find these guys? Well, these are properties. Again, the rule for finding unknown properties is, okay, what is my substance? I have nitrogen, that's an ideal gas. So do I have any way of finding specific volume for nitrogen gas based on the properties that I have? Well, remember nitrogen gas. So what are the rules for an ideal gas like nitrogen gas for finding specific volume? Well, somebody will say, well, what about table properties? Well, no, actually, your tables don't give you specific volume for an ideal gas. So for an ideal gas, I'm going to need some other tool for finding specific volumes, little v. I'm going to need some other tool for finding specific volumes for an ideal gas other than property tables. And notice I've said ideal gas at least 6 or 7 times now. That's intentional because the hope is eventually it's like, oh, well, what couldn't I just use the ideal gas? Yes. P1 V1 is equal to R T1 and P2 V2 is equal to R T2. Notice what happens if I set R in the middle here and I group like terms together. Well, let's just do this. Let's P1 little v1 over T1 is equal to P2 little v2 over T2. And go to the next sheet. Probably should have gone on the next sheet already, but we got through it. Now notice you can just solve directly for little v1 now. Little v1 is going to equal RT1 over P1. You can do that. And I can do the same thing for little v2. Right? Little v2 then is RT2 over P2. I can look up R in table A1, solve for V directly, and then take their ratio and plug the ratio of the values into this expression. Once I've got V2, then I just plug that in here and I can get the ratio of areas. Okay, so that works. Or notice that I don't actually need the specific values of the specific volumes. All I need is their ratio. Really, all I need is their ratio. So if I solve this expression here for their ratio, I need V1 over V2, which is going to equal, I'm going to group the like terms together. So that's going to put T1 over T2. And that's going to put then P2 over P1. And these are all known. Right? Both pressures, both temperatures, that's all known values. So that ratio is now a known value, or I can solve for these individually and then calculate the ratio, but in either case, once I've got V2 from the first law, this ratio becomes known. If this were a test problem, you are at at least 15 points at this point, probably closer to 17. You're basically at a C. You've shown me a clear path to a solution. If you'll go get R and C sub P values for me, right? If you go look up R and C sub P values at this point, and get them correct, then at this point, you're basically at 20 points out of 25 with me. And then it's just going and getting a solution in the right units, and we're set. Okay. All right. Let's look at a solution, shall we? I've got a solution in my PowerPoint slides, I think. Let's just go look at that. All right. So feel free to pause at this point and actually work this out, right? Actually work this out. Find C sub P, find your, well, actually, you don't even need your R value if you just go this path, right? So yeah, feel free to solve for V2, use V2 then in this equation, and then solve for the ratio of areas. And then so go ahead and pause here, work it out, and then come back. All right, you have a solution? Let's see how you did, okay? All right, so why is it not advancing? There we go. All right, so this one said instead of using specific heat, they said go ahead and use table properties, which is fine. Our tables in the Changle-Bowles text for anything other than air gives these properties per unit kilomole, which is fine. You just need to use then your molecular mass from table A1 to convert kilomoles to kilograms, right? For every kilomole, there's 28 kilograms of nitrogen gas. So that works. So I can then make these kilojoules per kilogram, and then these properties work out. So if I actually calculate that out, notice what I've got here. Now, something that the subtlety here is lost. It's real easy to just say, well, Steve, it's the metric units. Don't they just work out? Well, that's true until they don't. Anytime I've got kinetic energy, right? Notice the units here on the V1 is getting squared, right? So that's 200 meters per second. That's getting squared. That's meters squared per second squared. A meter squared per second squared is not a kilojoule per kilogram that I've got over here. These are going to be kilojoules per kilogram in the enthalpy terms. A meter squared per second squared is a joule per kilogram. So I'm going to need a factor of 1,000 to get rid of the meter squared per second squared and go to joule per kilogram so it can be combined with these enthalpy values. They're going to be kilojoules per kilogram. Okay, so just be aware of that. And if you calculate it out using table properties, you're going to get about 93 meters per second. Now, if you didn't use table properties, you can also get very close to that using what I talked about here, using C sub P at the average temperature. So at your given temperatures, you've got 7 and 22, which you're going to want those probably in metric units as like 295 and 280, right? So your average temperature is going to be like 287.5 Kelvin. So C sub P approximately at that temperature would be about 1.039 kilojoules per kilogram Kelvin. And then you run it through the same calculations. But again, anytime you're combining kinetic energy with enthalpy, whether it's English units or whether it's metric units, you're going to have to convert the kinetic energy values of meters squared per second squared to the enthalpy values of kilojoules per kilogram. Okay, so always be aware of this. In the metric units, it's a simple factor of 1,000. In the English units, it's like 25,000 or so. I think it's 25,037 BTUs per pound mass for every feet squared. No, 25,000 feet squared per second squared for every BTU per pound mass. Go look that up. It's in your textbook. Okay. Anyway, apply the appropriate units, solve it down. You should get about 93 or 93 to 94 meters per second. Either one of those is going to be correct. Perfectly good approximations. Okay, and then the problem also asked us to find the ratio of areas. Okay, as long as you use kelvins here, make sure you're using kelvins. Yes, it's just the ratio. So in theory, Steve, won't Celsius over Celsius cancel out? No, actually, Celsius is a relative scale. It does not work because what happens if you pick up a negative sign on one of these values? Now the whole thing blows up. You're going to get a negative ratio of volumes. That doesn't make sense. You have to use absolute pressures. You have to use absolute temperatures when you're working with the ideal gas law. You can't use gauge pressures and you can't use a relative gauge scale like Celsius or Fahrenheit. You have to use Rankine or Kelvin, and you have to use absolute pressures. There's no reason to assume the pressures given were anything but absolute, but you were given kind of a gauge temperature of Celsius in this case. So we do have to convert that to Kelvin. You can get they just computed the specific volume ratio directly here out of this solution. They said, hey, we've got algebra skills. We're not afraid to use them. And then plugging those in. Right? So we got V2 of about 93 meters per second, 93, 94, whichever you got will be just fine. Multiply by the specific volume ratio divided by the initial speed. And that will give you the ratio of variance. Um, for me, because I've been doing this a long time, I know my goal is not necessarily getting the right answer correct, which that is when you're actually working out in the real world, if you will. But for us, when we're trying to learn how to solve problems, I'm much more interested in, can you show me that you can, given an infinite amount of time, correctly solve the problem? If you do, I'm going to try really hard to get you to a B, but you got to show me that you can correctly and consistently get to somewhere where you could solve this out. And so it's, again, for us, that's why I stopped where I was at was, hey, look, I've got you a clear path to V2, and I've got you a clear path to the ratio of areas, right? Now, that's not going to get you an A if you just stop there, but it is going to get you probably a very high D or a very low C. And if you actually show me, how to get the properties like the specific heat, right? You actually go get me the specific heat and show me you understand you got to use Kelvin temperatures there. You're probably going to be at a B and actually get an answer, then that's going to get you to an A. That's how I grade. I know not everybody's going to grade that way. Um, some engineering schools are going to have different goals than I do. My goal is to make sure that you can show me you can solve problems. That's the only goal I really have. All right, guys. Hopefully that helps. We'll pick up the next example from there.